All right. Hello, everyone. Today, I am going over 5-4 enthalpies of reaction. Okay. Now, in this video, it's going to be a little different. Usually, I've just been putting up the one with all my info on it. I'm going to, again, like I always do, provide a blank one and one with all the stuff written in. So you'll probably have already seen this up there all finished, but the one that I have of the one that I have that's all written out, there's a lot of stuff like sort of jumbled around. So I'm going to make a kind of a cleaner version, cleaner copy of it. So I'm going to be adding stuff as we go through it. Okay. So 5-4 deals with what are called enthalpies of reaction. All right. And essentially what that is remember, enthalpy is talking about sort of like heat change. So basically what we're just talking about is like heat exchange that occurs during a reaction. So for a reaction, we have this generic equation, delta H, remember delta is change in. The change in the enthalpy for a reaction equals the enthalpy of the products minus the enthalpy of reactants, which makes sense because the products are the final thing, the reactants are the initial. So just like any other change in, you take the total of the final minus the total of the initial. Okay. The enthalpy change that accompanies a reaction is called the enthalpy of reaction or heat of reaction. So if you see those terms, they mean essentially the same thing. So enthalpy of reaction or heat of reaction is designated by the delta H sub Rxn. Okay. Consider the thermochemical equation for the production of water. All right. When they say thermochemical equation, the only difference between a chemical equation and a thermochemical equation is a thermochemical equation typically gives the delta H for the reaction over here. So they give us the equation for creating water from hydrogen and oxygen gas, right? And we get the delta H over here. Now, this amount right here, actually, I'm going to use a blue so it stands out a little bit, but not totally. This actually comes from this is the amount of heat energy that is either given off or absorbed during this reaction. So this is the it's like the I'm trying to think. Well, actually, technically, it's this. It's the H of the products minus the H of the reactants. Gives you that for the reaction. Okay. This equation tells us that this many kilojoules of energy are released to the surroundings. How do we know released to the surroundings? That's because our delta H is negative. Okay. This is important here. A delta H noted at the end of the balanced equation depends on the number of moles of reactants and products associated with the delta H value. So in other words, this delta H is specifically for the reaction of 2 moles of hydrogen gas reacting with 1 mole of oxygen gas and producing 2 moles of water. That's specifically for that amount. Okay. All right. Enthalpy diagrams are used to represent enthalpy changes associated with a reaction. If you had me for Chem 1 a couple of years ago, we did enthalpy diagrams. If we had me for Chem 1 last year, we did not because of COVID. So it'll be a little new. They're actually not hard at all, but I will show you guys how to do those. So in the enthalpy diagram for the combustion of H2, the reactants, 2H2 gas plus O2 gas, have a higher enthalpy than the product's 2H2O gas. This reaction is exothermic. Okay, so I'm going to actually down here, let me see, I don't know if I can zoom out, you can see this, but I'm going to actually, I'm going to draw the enthalpy diagram. It kind of talks through it here. It's what it's, that's what these kind of bullet points are. So an enthalpy diagram, you have sort of like you're creating an X and a Y axis. Okay. On the Y axis, this is enthalpy. Your delta H. Okay. And down here, this is generically time. This just shows essentially time going forward. Okay. And you'll see when I put the stuff in here what that means. So enthalpy diagrams are used to represent enthalpy changes associated with a reaction. Okay, so if we look at the reaction that they gave us up here, this reaction, okay, what do we know about it? Well, we know from the delta H, we know that it gave off energy, right? So there's some stuff that we can, by looking at the delta H, there's some stuff we can gather from this. So I'm gonna write it down here in bullet points. So if the delta H is less than 0, negative, then your reactants have a higher heat quantity, have a higher enthalpy than your products do. Okay. Because essentially what that means is from the reactants to the product, energy was lost. So that means the reactants had to have more energy than the products did. Okay, and then the opposite is also true. If your delta H is greater than 0, positive, then your enthalpy of your reactants are going to be less than the enthalpy of the product. In other words, heat was absorbed or gained. Okay. So if we look, then using that, if we look at what we have here, we know that because our delta H is negative, our reactants had more enthalpy than our products. Okay, so over here, now I guess I might have, this might be slightly, really not a big deal, but just to be very, very precise. Okay, that represents the enthalpy in H, not the change in enthalpy is technically the difference between 2 points. So, okay. So, anyway, we know that our reactants have more enthalpy than our products. So what we're going to do is we're going to write our reactants. Now the reactants start kind of on the left side here. So we're going to write the reactants from our equation, 2H2 gas plus O2 gas. Okay. So we write that here, and it's going to be higher up. Now, we're not using any exact numbers right now. Okay, we're not using exact numbers on this. We're just showing a relative comparison. Okay. So the reactants are always going to go to the left of the products, because as time advances, what happens? You go from reactants to products, right? You've got a reaction occurring. So the reactants will always be to the left of the products. Now you have to figure out which one is going to be higher up. If your delta H is negative, your reactants are higher up because they have a higher enthalpy, and your products have a lower enthalpy. So we always draw the arrow just like in the equation. The arrow points from the reactants to the products. So in this case, it's going to point down. Okay, and then we write our product or products down here. 2H2O gas. Okay. So notice, just like the equation, the reactants are kind of on the left, products are on the right. Arrow goes from reactants to products. The reactants are higher because our delta H is negative. So that our reactants are higher than our products. Okay. That's the enthalpy diagram. And the only thing left is over kind of to the right over here. You're just going to do delta H. You're just going to write the delta H in. Delta H equals negative 483.6 kilojoules. Okay. This is the enthalpy diagram. All right. Okay. So that covers this stuff. Enthalpy is an extensive property. You have extensive and intensive. Extensive means therefore the magnitude of enthalpy is directly proportional to the amount of reactant consumed. So in other words, the amount you have of it does matter. Okay. For example, if 1 mole of CH4 is burned in oxygen to produce carbon dioxide and water, 890 kilojoules of heat is released to the surroundings. If 2 moles of CH4 is burned, then 1,780 kilojoules is released. The sign of, so that all they did was then, like in this example here, they're using this equation. If this is for 1 mole of this, if you put 2 moles, then you multiply this by 2, because this is the amount for 1 mole of CH4. Okay, I'll show you that in some math here in a little bit, but the sign of the delta H depends on the direction of the reaction. So if you flip the reaction, so in other words, we've got CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O liquid. Then we've got delta H equals negative 890 kilojoules. If you flip the equation around, flip the reactants and the products, you get the same amount, but it's just the opposite sign. Your delta H now becomes positive. Okay. Enthalpy change does depend on state of matter, because as you change states of matter, it gains or loses energy. So in other words, you can have 2 moles of water as a gas turning into 2 moles of water as a liquid, a state change. That's not really a reaction, not a chemical reaction, just a state change, but it will lose energy because you can gain or lose energy just by changing state of matter. Right? Okay. So I think, okay. So I'm going to stop here. This is for the notes. That's all we really had for the notes, but I am going to do some practice problems on a second video. All right.